Alright friends. Friends, today I am going to talk about the risers. What are risers? Risers, if I ask you, you might say, sir, riser is a reservoir of molten metal which is used during the solidification, and it compensates the shrinkages happening during the solidification, right? But my question to you, the next question I would ask is that where the risers are located, by the way. You will say, sir, it is in the same casting. It is present in the same flask, right? Then I would say that you are telling me, you are saying that the casting is going to solidify, but the risers are not going to solidify because they have to supply extra molten metal to the casting, isn't it? Now, don't you think that it is somewhat unfair to the riser, because it is also a element in the same flask and it is made up in the same with using the same ingredients as that of the casting cavity, and you are expecting the riser not to solidify but the casting to solidify so that riser can supply extra molten metal to the casting during the solidification, right? So it's confusing, right? Now the second point I want to make is that if many times I ask people that what is the use of the riser, sometimes they also give the answer, sir. Apart from compensating the shrinkages happening, it is just a byproduct of riser, but the main function of the riser is to act as an indicator that the cavity has been filled up. Many times I have heard this answer from people, right? Because when you are going to pour the molten metal is going to fill the cavity first, and then it is going to rise above the riser, and when it starts to come out of the riser, we expect, or we infer that yes, the cavity has been filled up completely, right? So there are many notions and many ideas and many confusions as far as risers are concerned. So here we are going to talk about that itself, and riser design is also one of the most important topics from metal casting as far as gate is concerned, right? So we are going to focus upon riser as of now, and so yeah, let us start. So before starting, let me tell you that just now we discussed that risers are there to compensate the shrinkages. Then why these allowances are used for, right? I'm repeating my question once again, that just now we discussed risers are there to compensate the shrinkages happening in the casting cavity during the solidification. Then why the allowances are for? Because allowances are also used for compensating some kind of shrinkages happening or some kind of changes occurring during the solidification of the molten metal, right? So what is the difference between allowances and the risers? Are both of them provided together, or one at a time? Suppose allowances is provided and risers are not provided, or vice versa. Now what is the thing? Let me clarify you with a small example. You can see that I have one slide over here on your screens. You can see that the shrinkages, we are going to talk about the shrinkages. Now the story is going to begin from a point where you have already poured the molten metal into the casting cavity, and now what is the state of that molten metal? It's in liquid state, right? It is in liquid state. Now our story begins from this point, that the molten metal is in liquid state now, and now from here onwards it is going to start its journey to the solidification. Getting the point? Yes. Now, this molten metal, which is in liquid state, what could be its temperature? Let's say this metal that we are going to cast, it's let's say 500 degrees Celsius is the melting point of this metal, some XYZ metal, right? Firstly, the question arises: are you going to I'm going to talk about this molten metal at liquid state, but what is its temperature? Is it just 500 degrees Celsius, or it is even higher than that, or it is lower than that? Obviously, the answer is higher than that. higher than 500 degrees Celsius, right? Fine. But how much higher? That is again a question, right? Now let us say it is let us say that it is 700 degrees Celsius is the pouring temperature. Okay, pouring temperature. So I have poured the same metal which melted at 500 degrees Celsius. At 700 degrees Celsius, I have poured it. Right now, one small piece of information since we are discussing about this, that what is this extra temperature or the heat that you have imparted is known as, because you could have poured at 5 degree also, right? But you have increased the temperature to 700 degrees Celsius. So what is this extra amount of heat known as that you have imparted to the molten metal now, right? So it is known as degree of superheat, my friends. Just a small piece of information since we are discussing about this. So it is known as degree of superheat. Okay. It is known as degree of superheat. Right. Now, let us start our discussion from here. Molten metal at 700 degrees Celsius, it is in liquid state obviously. Now it is going to lose its latent heat. Latent heat or sensible heat? No, it's not latent heat, it's sensible heat, right? Because sensible heat is the heat that is rejected or absorbed in the same phase, right? There is no phase change as far as sensible heat goes. So you can see that molten metal cools down to freezing temperature, right? That too in liquid state. That means from 700 degrees Celsius, it is rejecting heat and it is cooling down to 500 degrees Celsius. Got the point? So for the first stage of solidification, let us call it first stage number 1. And now, what is going to happen at this temperature at 500 degrees Celsius? It is going to change its phase, right? It is in liquid state right now, and now it is going to change into solid state, right? It is going to change into solid state. So that means it is going to lose some amount of heat also once again, right? Now, what is that heat is known as? Where the phase change occurs. Of course, latent heat. Yes, you are absolutely correct. It is latent heat. And now you can see that the solid we have formed is at a temperature of 500 degrees Celsius, right? So you have seen there is a second stage of solidification. Let us call it second stage, right? And now from freezing temperature solid, it is again going to cool down to room temperature solid, which is, let's say, 25 degrees Celsius. Is the room temperature. So you can see from 700 liquid to 500 liquid, from 500 liquid to 500 solid, and then 500 solid to 25 degree solid is the journey our molten metal is going to travel. Now what to discuss about? We have understood there are 3 stages in the solidification. Fine. Now what is first stage known as? Let me call it liquid contraction, because first stage, let me call it liquid contraction, because there is interference of liquid. Second stage, what do we call it? Let us call it liquid shrinkage once again, or liquid contraction once again, right? So you can see that there are 2 stages of liquid contraction I have named. Now what is the third stage? Third stage is completely solid, so there is no point of liquid contraction, it is solid contraction, right? So what we have seen is there are 3 stages: liquid contraction 1, liquid contraction 2, and solid contraction 3, right? So 1 and 2 are liquid contractions. Is solid contraction. Now why are we discussing about this? We are discussing just to understand, my friends, the concept of the riser. Alright. So you have, as we have already discussed, we don't have to repeat it once again. So liquid contractions are going to happen in these 2 stages, and who is going to compensate for this contraction? Suppose, let me take an example. Suppose you want a cube of 10 by 10 by 10 centimeter dimensions, right? Now, if this liquid contraction is happening at 1 and 2 stages, first and second stage, and if you are not going to compensate it, what is going to happen? It might shrink down to 8 by 8 by 8, Just an idea, just an example, right? So it will shrink down to 8 by 8 by 8, but what was my required dimension? It was 10 by 10 by 10. Now who is going to compensate that? My friends, here in this case, just to compensate this extra, this contraction, we use risers. Getting the point? So we are going to use the riser for first and second stages that are known as liquid contractions. So riser is going to supply extra molten metal whenever this liquid contraction is going to happen. Understood? It's beautiful. And then solid contraction. This solid contraction is because now riser can supply only the molten metal, right? But in the third stage, in solid contraction, there is no liquid metal's role, right? So what we can do, we can provide the allowances here, right? So we provide the allowances in the pattern. Suppose let us take the example of shrinkage allowance, which is nothing but the contraction happening when the molten metal, not molten metal, the solid at 500 degrees Celsius shrinks or cools down till 25 degrees Celsius in solid state only, right? So there is also going to be contraction is going to happen, and who is going to take care of that? Allowances are going to take care for that. So what we have understood is that in first and second stages, risers are helpful. They take care of all the contractions, and here allowances take care of the contractions. Very good. So this we have understood. Now let us move to the next topic, which is what? Which is the gating system. Because riser, as you can see on your screens, that in this slide you can see the gating system. Riser is a small element in the gating system, right? So what is the gating system? First of all, gating system is nothing but it is the path followed by the molten metal to reach the mold cavity, basically, right? And so you can see that we start from pouring basin, sprue, runner, ingate, and the risers. So we have not included the cavity because that is the obvious thing, and we have included riser also. Yeah. Now we are going to skip all these things: pouring basin, sprue, runner, and ingate, because we just want to focus upon the riser as of now. All right, right. Right. Okay. Now, my friends, I want to discuss with you the concept of the riser. Once again, I'm going to raise this point that because riser is the same element in the same flask, it is made up of the same ingredients, but still you are expecting riser not to solidify first because it has to take care of the liquid contractions happening in the casting, right? So how we are going to achieve this? Because it sounds very unfair to the risers, right? You are giving all the relaxation to the casting, but you are being unjust with the risers, right? There is no freedom for the riser. So what to do? Firstly, what we will do is, before proceeding further, I want you to have a look at the, at a small video clip I have brought for you, which is about the riser. It will give you an idea like how the risers are located, and then based upon this concept, this understanding, we are going to build the story. All right. So yes, so we can see over here on the screen that right. So you can see that there is a furnace, and we are melting aluminum here. So I just want you to have an idea like what risers look like, okay, and where they are located like that. Although it is just a small example, it is a very rudimentary, very basic example I could give you. Okay, so you can see that they have already prepared one cavity, and from one side they pour the molten aluminum, and you can see from the other side something came up, right? Actually that is nothing but the riser. So, and when the molten metal came out of it, we immediately stopped pouring, because it was an indication that yes, our mold cavity has been filled up, right? It is just an additional function, my friends. It is not always the case, okay? And now we are going to break the mold, and now you can see that you can observe the pouring basin, sprue, runner, ingate, and also the mold cavity, the casting, and then the riser. You can see two vertical things, right? So those were one was pouring basin and sprue, and another was the riser, all right? And what we did later on was that it was not required, so we have chipped it off, right? We have chipped the pouring basin, runner, ingate, and the riser thing, just the casting we have, okay? So I hope that you have got a little bit of idea that like where the risers are located and how they look like, right? Now we are going to discuss upon this. Fine. So now, okay, coming back to the same topic, that how you are going to achieve the this quality of the riser, that it should not solidify before casting, right? So for that, what are the requirements? Can you tell me? Can you think of any requirements, or what are the factors or the parameters upon which the solidification would depend upon? Yeah, you're following? My question to you is, what are the parameters upon which the solidification depends upon? So what I can think of is that, sir, I have always observed that whenever I want to cool down something, what I do is I increase the surface area. Okay, I increase the surface area of that particular component, and so that it can easily conduct or convect its heat, and it becomes cooler, right? Fine. So by increasing or by suppose decreasing the surface area, we can reduce the heat transfer. We can reduce the heat transfer from the riser. Fine. Now there is something called volume also, right? Because I can obviously, which one is going to take a shorter time to cool down? Just a small cup of, suppose a small tumbler is there, a glass of water. Suppose let us take a hot glass of water. You have poured extremely hot water into that glass, and there is a bucket of the same temperature of water. Which one is going to solidify first? Obviously the tumbler, because it has a smaller volume, right? Yeah, so what I can see is that the volume, if volume is high, or let's say it's smaller, the solidification time, okay, I will be telling you what is solidification time. Solidification time is going to be smaller. Now, what is solidification time? It is the time taken to solidify, that's all. It is the time taken by anything, by the casting or by the riser or by anything to solidify. It's fine. So what we have understood is that the solidification time is going to depend upon two things, surface area and the volume. Okay, so I am going to write the same thing over here, that the solidification time, okay, let me represent it by tau, and it depends upon volume by surface area. If the surface area is more, then the solidification time will be less. So they are inversely proportional. If the volume of the substance is more, it is going to carry a huge amount of heat with it, and that is why the solidification time will be higher, right? And okay, so these are the factors that it depends upon, but I will be telling you more about it. There is a rule for, there is an expression for solidification time, which also looks something like this, but it is not exactly like this. Okay, so this is just for your sake of understanding. Very good. So we have understood one basic thing, that we have to decrease the surface area. Now, what is going to be the volume of riser? What is the volume of riser? How to determine the volume of riser? My friends, there is something called shrinkage volume. I want to tell you something about shrinkage volume. Okay. See, just now I told you that there was a cube of 10 by 10 by 10 side, and it shrinks by 8 by 8 by 8 if you don't employ a riser. right? That means what is the total reduction in the volume? Let us see. Suppose 10 by 10 by 10 was the required dimension. That means 1000 mm cube. Okay, and now we have got 8 by 8 by 8 in absence of the riser. So it is 8 cube means how much? It is 512, right? It is 512 mm cube, right? Now what is the total reduction in the volume? So that we call it shrinkage volume, okay? We call it shrinkage volume. We call it shrinkage volume. Shrinkage volume is nothing but it is the volume by which it got contracted and we lost the dimension, because of which we lost the dimension. So 1000 minus 512. Okay. So you will see it comes out to be around how much? Okay. So it comes around 488 mm cube. Getting the point? So this much is your shrinkage volume. We call it VSC. Okay, we give it by VSC. It is the shrinkage volume 488 mm cube. Right? That means the riser has to supply 488 mm cube. Understood? Now, sir, is the volume of riser going to be exactly 488? What if riser also got solidified by a little amount? Yes, wonderful question, wonderful doubt actually it is, right? So what we will do is, actually there is a usual practice that the shrinkage volume is never kept as the exact shrinkage volume, okay? It is taken as thrice, minimum thrice of the shrinkage volume, okay? It could be 4 times or 5 times of the shrinkage volume, but never going to be lesser than thrice of it, right? So the volume of riser is always equal to or greater than, it is kept as thrice the shrinkage volume. Okay, like this. So the volume of riser, it has to be at least thrice the shrinkage volume, right? So if it is thrice the shrinkage volume, that means volume of riser can be computed as 3 into 488, which is 1464. Okay, so 1464 mm cube is the volume of the riser which is fixed. Getting the point? So now our main discussion is going to start that, sir, if volume of the riser is known to you, then what? Fine, you have told that it is going to be thrice the shrinkage volume, fine, but what is going to be the surface area? Because the surface area is the one which is also playing a very important role, in determination of the solidification time, right? So what is going to be the surface area? Now, sir, you also told us that surface area has to be minimum in order to minimize the heat transaction, isn't it? Yes, of course it is. Now, how do we get to know that which surface area is the least, so that we can reduce the heat transfer? That is again a good question, right? So what we have to do is we have to select such a design or such a geometry of the riser which can provide the least surface area for the given volume. So one thing is fine, that we have understood what is the volume, and on the basis of this volume that we have got, we have to design the geometry such that the surface area of that geometry is least. Got the point? So we can reduce the heat transfer. Very good. Okay. Now the first thing that comes into our mind, the first geometry is I think the sphere. Okay, because sphere gives me the least amount of surface area for a given volume. Now, sir, how do you know this? I know because I have there are proofs for the sphere, right? And it has been experimentally found out for a given volume, sphere gives the least amount of surface area. Fine. Now, it also has the proof in nature also, my friends. Okay, let me give you a few examples. Have you ever observed those small sparrows, right? Those sparrows, especially during the rainy season, Okay, so what happens that you must have seen, you must have observed that some birds while flying they become drenched because of the rains, right? And they are totally wet and they feel cold. So they might be sometimes they would be coming to your window panes. They would be sitting on the window panes. And have you ever observed their how do they look like? So they what they do is they puff up their the air in between their feathers, and they look completely spherical. Okay, almost they try to achieve a sphere kind of thing. So what are they trying to do? We don't know, right? Okay, next example. Have you ever seen small puppies, dog puppies, right? Yeah. So what they do is, suppose when they feel cold, have you ever observed how do they sleep? They will sleep by curling themselves up, and they become like a. They also try to achieve the spherical dimension. Okay. Although they can't because of their own shape, their own geometry, but they try to fold their hands and legs and limbs, and they try to become as spherical as possible. Why are we talking about the animals? Let us consider yourself. Take the example of yourself. Suppose you went to a hill station, you don't have much warm clothes, and still you're feeling cold. Then what you will try to do? You will simply, put your hands over here, and you will also fold your legs, and you will also curl up, right? So actually what you're trying to do is you're trying to minimize your surface area by achieving the spherical dimension, right? Although we can't because we have our own geometry, but this is what we all try to do. Getting the point? It's a beautiful thing, by the way, let me tell you. So even if you watch birds, let us take the example of birds or dogs or even humans, everyone tries to minimize the surface area whenever they feel cold by trying to achieve a spherical shape. Got the point? Fine. So now let us forget about those examples. That was just for the illustration, for the correlation. And now we are going to talk about the rises once again. So what if, sir, why I understood the minimum surface area is going to obtained in the sphere, then let us make the rises spherical. Fine, we make it. Then what will happen, although the spherical riser is going to hold that material, that molten metal, for a very, very long time in molten state, mind it. But I'm not saying that molten metal in the riser is not going to solidify at all. No, we are not saying that, right? We have already taken that into consideration. That is why only we are considering thrice the volume of the shrinkage volume. Getting the point? Because of course, it is going to solidify. And the very first moment when it is going to solidify, let me show you with the figure here. Suppose this is the spherical riser. Okay. Now what will happen, the very first time, suppose it is filled up with molten metal. And when it is going to solidify the first, it will solidify from the periphery. Okay. This periphery is going to solidify first. It is going to solidify from the periphery. Now I hope that you have got the challenge, right? Because it is going to block the exit. It is going to block the path from where a riser was supposed to supply the molten metal. Isn't it? The complete point is gone. The purpose is gone. So now what to do? Then we might have to change the geometry, isn't it? Very good. So this spherical riser, although if you talk about if you talk about the molten metal at the core of the riser, this is going to stay in molten state. This particular part is going to stay in molten state for a very, very long time, because of course these spheres have minimum surface area, and that's why the heat transaction is the least, right? So this at the core is going to be in molten state for a very long time, but it is of no practical use, right? So the purpose is gone. Now what to do? So no spherical riser. The next geometry that we can go for, the next best is, I think it is the cylindrical riser. Okay, fine. So you say cylindrical riser, it is good. But this cylinder, suppose, Okay, let me take the example of this water bottle here. See, this water bottle has two dimensions. Sphere has just one dimension, the radius or the diameter. But here there are two dimensions, the height and the diameter. Now, sir, if you want to minimize its surface area, right, don't you think that you need to find a correlation between the diameter and the height, or some value of diameter and the height, so that this cylinder is going to provide the least surface area for a given volume? Yeah, it's a fair point. What you're saying is a fair point. Then now what to do? We have to find the correlation between diameter and the height. Okay, so this is what we are going to do right now, right? So just in brief, what we have discussed is that we have got the volume of the riser, which is 1464 mm cube. By considering a small example, I considered an example that I want to cast a cube of dimension 10 by 10 by 10, which is the 1000 mm cube. And now when it got reduced, okay, or you can do one thing that, mm cube is very small. You can consider, okay, fine, let it be. Anyways, it is just an example. So 8 by 8 by 8 is 512 mm cube. That means the shrinkage volume is 488 mm cube, right? And now we have to build a riser so that it can compensate thrice its volume, thrice of this volume, which is which volume? Shrinkage volume. Okay. Why we are providing thrice of the shrinkage volume? Because there are going to be certain solidification in the riser also. Riser is also not 100% efficient. It also has some losses. So whenever the losses are going to take place, this extra provision that we have got is going to be enough for that, right? And so we have got 1464 mm cube, and then we wanted to minimize the surface area for 1464 mm cube. The first design you saw was the spherical riser, which did not work out, and now we are approaching towards the cylindrical riser. Okay, now, okay, fine. When you talk about the cylindrical riser can be placed in two manners. Okay, so what are those? Let us have a look. First one is your top cylindrical riser. Okay. Top cylindrical riser. Now, what is the top cylindrical riser, sir? And how does it look like? My friend, it looks like this. Suppose the height is h and the diameter is d. Here. Right? So this is your top cylindrical riser. Okay, fine, sir. It is a top cylindrical riser. What we have to do now? We have to minimize the surface area, right? And for which, what we are going to do is, we are going to start with the volume. Okay. Now, what is the volume of this riser? Could you tell me? You know, its volume of a cylinder is pi by 4 d square h. It is pi by 4 d square h, right? Yes, it is pi by 4 d square h. And this is the volume of the riser. Let me call it VR. Fine. Now, since we want to minimize the surface area of this riser, let us have a look at the surface area from which heat transition is taking place. Okay, so from where the heat transition takes place, man? The heat transition takes place from this side. Yes, it takes place from this side. From here, of course, here, from here, and from here, from the top. Yes, sir. Of course, from the top also it takes place. But from over here, no, sir. It cannot take place from here because this is the entire casting and this is the riser you are telling me. Okay. I'm sorry that I forgot to describe about this diagram. So this diagram actually indicates the casting over here. This bottom portion is the casting itself, and at the top of which there is a cylindrical riser we have kept. Okay, and yes, so we have to. Yeah, so molten metal is completely present in this entire geometry. Assume the molten metal is completely filled in this entire geometry. Okay, yeah. So it cannot exchange heat within itself, isn't it? It cannot. So we have got three surfaces from where the heat transaction is taking place. Okay, so I'm going to write the same over here. The surface area is, what is this side? Because this side is nothing but it is the walls of the cylinder, isn't it? The wall of the cylinder. So it is nothing but the pi dh. The surface area of this wall of the cylinder is pi dh, isn't it? Very good. And okay, what about the surface area at the top? It would look like a circle, isn't it? It would look like a circle. Now, what is the area of the circle? It is pi by 4 d square, isn't it? Pi by 4 d square. That's all. So pi dh plus pi by 4 d square, that's all. Fine. Now, since we have to minimize the surface area, don't you think we can perform maxima and minima thing here? Of course we can. But, okay, for minimizing, what we need to do is we have to differentiate the surface area with respect to one variable, isn't it? Fine. Now, what is that variable? Is it d or h or pi or 4? Forget about pi and 4. We have to select between d and h, right? But d and h both are variables. They both are variables. Because that is the whole concept, right? That is the whole idea about our discussion, that we have to determine a relationship between the diameter and the height so that we can specify one cylinder. Because to specify this cylinder, we need two dimensions, one diameter and one height. That's all, isn't it? So that is what we are trying to do. But we cannot differentiate this entire equation if there are two variables. Then what I'm going to do, I'm going to replace one variable with a constant. Okay. Now, how we are going to do that? I'm going to replace this h. Okay. This h. And what is this h can be written as? I'm going to take the help of this first equation here, which is h is equal to 4v by pi d square. Okay. Let us write v itself. It is simple. Yeah. So h is equal to 4v by pi d square. Let us replace that, substitute it. So pi d into 4v by pi d square plus pi by 4 d square. Yeah. So what I can see is this pi gets cancelled out, this diameter and diameter gets cancelled out, and what I get is 4v by d plus pi by 4 d square. Okay, 4v by d plus pi by 4 d square. Is it okay? So this is fine. Now I can see that only two diameters are there and both are variable. So I can differentiate the surface area with diameter. So what do I get in after differentiation? It is minus 4v by d square plus 2 pi by 4 d. And also you know that we equate it to 0, right? Differentiate and equate to 0. So yeah, we have differentiated and now equating to 0. You will see certain things cancel out. This 2 and this 4 gets cancelled out. So what I get is 4v by d square equal to pi by 2 d. Okay, or we can write it as d cube is equal to 8v by pi. Okay, fine, fair enough. Now, what I'm going to do is I'm going to resubstitute the value for volume here. Okay, So d cube is equal to 8 by pi into v. Now what is v? It is the same thing, pi by 4 d square h, pi by 4 d square h. So pi and pi got cancelled, 4 and 8 got cancelled, d square and d cube got cancelled. So what I get? You can see that I am left with one relationship between d and h, which is d equal to 2h. d is equal to 2h. d is equal to 2h. Right? So what we understand from here is that if your riser looks like this, that means if your riser is a top cylindrical riser, that means when the heat transaction is going to happen from only three surfaces, that three surfaces means actually it is nothing but the two surface only. Let's say three sides, okay, and yeah, so there the relationship between diameter and height goes like this: d equal to 2h. Got the point? So this is for your top cylindrical riser. I hope that you have followed this. And now I'm going to try with another kind of riser, which is known as side cylindrical riser. Okay, I'm going to try it with side cylindrical riser, and let us have a look like what diameter and height relation goes over there. Right? Okay. I give you some time to note it down. All right, friends. So after discussing about the top cylindrical riser, now it's time to discuss about the side cylindrical riser, and we are going to perform the exact same thing what we did for top cylindrical riser. Alright, so here what we have to do is, let me show you how it would look like, right? For side cylindrical riser, the diagram can be made like this. Okay, so side cylindrical riser looks like this. So what is happening here is that there is a casting cavity here, and there is a riser, and it is completely filled with molten metal. And obviously it is in a flask. Okay, it is surrounded by the sand, and now we have to calculate the relation, or we have to find out a relationship between diameter and the height. Where? So you will see. Let us start with the volume once again. You can see volume of the riser is again pi by 4 d square h, and the surface area we have to calculate is nothing but it is that area from where heat transaction is taking place, not the exact or actual surface area of the riser. No. What is that area from where the heat transaction is actually taking place? And you can see that here heat transaction happens from the sides, isn't it? Yes, we agree. From the top, of course, okay. And from the bottom also, can we see? Is it happening? Yes, of course it is happening from the bottom also, isn't it? So what we can see is the surface area is going to change here, and the entire process remains same exactly as the previous one. Okay, so the surface area will become pi dh, which is the surface area of the cylinder at the from the wall, and then 2 times of pi by 4 d square. So what I can see is this gets cancelled out, and I have the surface area as pi dh plus pi by 2 d square. Fine. Now, can we differentiate this equation directly? Can we differentiate this equation directly? No, we cannot. Why? Because there are two variables. One is diameter and the height, right? So we have to change this. We have to replace this height from here, and it is h is equal to, it is 4v by pi d square. Okay, it is 4v by pi d square. So let us put this same thing here. So as is equal to pi into d into 4v by pi d square plus pi by 2 d square. right? So pi and pi got cancelled, d and d got cancelled. What we are left with is 4v by d plus pi by 2 d square. So fine. Now let us differentiate now, because we have got only one variable here. So ds by dd, if we differentiate this thing, okay, let me write in the next line. So das by dd is minus 4v by d square plus pi by 2 into 2d equal to 0. So 2 and 2 got cancelled here, and so 4v by d square is equal to pi d we have got. So if you have a look, you can see d cube is equal to 4v by pi. Now can we put the value of v here? Yes, of course we can do that. So d cube is equal to 4 by pi into pi by 4 d square into h. So pi and pi got cancelled, 4 and 4 got cancelled, d square and d cube got cancelled. So what are we left with? We are left with the result, which is d equals to h. D equals to h. Yeah. Now what is d equal to h? It is a relation that we were seeking for, right? So what it does it signify? It signifies that in case of side cylindrical riser, which looks something like this is an arrangement. If this is your riser, then what is going to be the relation between diameter and height in order to reduce the surface area, to make it minimum, right? To minimize the surface area. This is going to be the relationship. I hope that you have understood. Yes? Very good. We have seen the concept of minimization of the surface area for top cylindrical riser and side cylindrical riser. And now I'm going to tell you about the 4 conditions that we have already discussed already. There is nothing new. The only thing is that we are going to segregate that what we have learned and in the form of conditions. Okay. So the riser design, if you talk about the riser design, the first condition, condition number 1, is known as the necessary condition. Okay, necessary condition. What do you mean by necessary condition? Necessary condition means until unless this condition is satisfied, you cannot design the riser. So first and foremost thing that you need to look after the riser while designing is that the fulfilling this condition. And what is this condition? It is that the volume of riser has to be greater than or equal to thrice the shrinkage volume, right? It has to be thrice the shrinkage volume. Very good. And which is known as necessary condition. So once this condition has been satisfied, once you have made the riser thrice of the shrinkage volume, we will move to the next condition, which is condition number 2. And it is known as the sufficient condition. It is known as sufficient condition. And what it is? Sufficient condition means that the solidification time of riser has to be greater than that of the casting. It cannot be smaller than casting. Mind it. Now what is solidification time? I told you it is the time required by the riser to solidify. Right? So the time taken by the riser to solidify has to be greater than that of the casting. The riser should solidify at the least, at the last, isn't it? Now the third condition is your necessary condition, sufficient condition, and now the location of the riser. Okay, location of the riser. Now, location of the riser. So, location of the riser has to be, the riser has to be placed in such a manner, at such a place, from where the molten metal could be delivered very easily, effectively and efficiently, wherever it is needed the most. Wherever it is needed the most, molten metal can be transferred from the riser to that point very easily. So accordingly, you have to locate your riser. So this is your third condition, right? And now the fourth condition is the shape of your riser. Now what do you understand by shape of the riser? Just now what we have discussed is that it should be able to provide the least surface area for a given volume. If the spherical riser is not working out, then we have to go for the next best, which is nothing but your cylindrical riser, right? Very good. So these are the four conditions that we have to fulfill for the riser design. Okay. So yes, you can note it down, and then we can move to the next point. Now, my friends, you have seen there are four conditions to design a riser, right? Without which the riser will not function at all. Okay, so that you have understood. And now what we are going to discuss is that we are going to discuss about two methods. What are those methods? These are the methods of the riser design. Sir, what we have understood is not a method? No, my friend, it is nothing but those are the conditions. Those four are the conditions for the riser design. Now we are going to talk about two methods of riser design. And these two methods are known as Keynes method and modulus method. Okay. Keynes method and modulus method. Right. Okay. Now, what do you understand by Keynes method and modulus method, and what are they? My friend, Keynes method is nothing but it is one method which was developed in order to ensure that whatever the riser you have designed, by keeping all these four conditions in mind, is it going to be really functional, or is it going to be really helpful for your particular casting? Okay, so it is just like a cross-check kind of method that they have developed. Whatever the riser you have designed, is it going to work out or not? That can be checked using these two methods. Okay, Keynes method and modulus method. So what Keynes method says is that the adequacy of the riser can be judged by comparing it with against a graph. Okay, now what is that graph? He gave one graph, and where this x-axis indicates the freezing ratio. Okay, it indicates freezing ratio. Okay, fine. Now what is freezing ratio, sir? I am going to tell you about that. Next is in the y-axis volumetric ratio. Now again, so what is volumetric ratio? I am going to tell the same thing again. Okay, okay. Now what he did was that he made a graph, and it looked something like this. Something like this. Okay, it is again a freehand figure, so it might differ from the actual diagram. And what he said that if you are going to calculate the volumetric ratio and the freezing ratio for your riser design and the casting design combination, and if suppose the volumetric ratio is something like this and the freezing ratio is something like this, and if they meet at this point, that means they are meeting at this point, that means if they are meeting at the right side of the curve here, that means that ensures the adequacy. That yes, your riser design is going to work because this point is lying on this side of the graph. Okay, I'm giving you just an introduction, so just to make you understand, right? And suppose your volumetric ratio for some casting came out like this, and the freezing ratio came out like this, and they met at one point over here, and now since this point is lying at this side, It is not adequate. It is not going to work out according to Keynes method, it says. Are you getting the point here? So this is nothing but the Keynes method. Okay. Let me give you what volumetric ratio and what is freezing ratio so that you can understand it better. Alright friends, so listen up now. Once again I am repeating what is Keynes method. Keynes method is again a small method to judge whether the riser is going to work out or not, and for that we use a diagram, a graph with VR, volumetric ratio on the y-axis and freezing ratio indicated on the x-axis, and there will be a graph like this. And if your meeting point lies on the right hand side, that means it is adequate. Over here on the left hand side, not adequate, not going to work out at all. You need to redesign it. Now, what do you mean by volumetric ratio? That has been indicated over here at y-axis is nothing but the volume of the riser by volume of the casting. Okay, volume of the riser divided by volume of the casting. So it is a ratio between riser volume and the casting volume, right? So you must be getting some y value, let's say some y value you get. And in freezing ratio, what is freezing ratio? It is the ratios of surface area to volume of casting to surface area to volume of riser. Okay, so surface freezing ratio is nothing but surface area divided by volume. Whose surface area? Whose volume? Casting's volume and casting surface area. Similarly, surface area by volume of the riser. Take the ratio, get some value, let us call it some x value you have got, plot it over here, some y value you are going to get, some x value you got here. They meet at this point. Since they lie over here, that means it is adequate. Adequate. Okay, that means it is going to work out. And if, or let's say, because it is adequate, that means the casting will be sound casting. The casting will be a sound casting in this case. And if it lies over here, let us call it y dash and x dash. And if it lies over here, of course, it is going to shrink. I mean, the casting is going to shrink. Riser is not going to help it. So you will get a shrink casting. Okay, you are going to get a shrunk casting. Yeah. So this is nothing but the Keynes method, right? Now let us talk about the modulus method, which is the next method of riser design. We have understood the Keynes method of riser design. Now we are going to move to the modulus method of riser design. It is another method, and why it was developed? Because Keynes method was found out to be a little complicated and time consuming, and yeah, so that is why they came up with another method called modulus method to check the adequacy of riser. Okay, and it is based on one law or a rule that was given by Kovrinov's. It is known as Kovrinov's rule. So Kovrinov's was a was an engineer, and he studied the solidification of the molten metal, and he gave that this solidification rate or solidification time, the time taken by anything to solidify, depends upon these things. He said that the solidification time depends upon Cm and V by A ratio, like this. He said like this. Okay. Now this tau stands for solidification time. Cm stands for a constant which is nothing but the mold constant. Okay. It is a mold constant. Cm is known as mold constant. It depends upon the mold material. And V is nothing but the volume of what? It could be of anything. It could be of casting or it could be of riser. Right? Whosever solidification time we are determining. It is the volume. And what is this? This area. This is area. So cross-sectional area, surface area. It should be surface area. It is surface area of riser of any casting. Anything. Now what he said that this V, he actually, V by A ratio, he called that V by A ratio is nothing but, let me call it a modulus, okay? So he said, I'm going to call V by A ratio as modulus. Modulus. And he said that if a casting or a riser or any body has modulus, has a higher modulus, what does it mean? It means that it is going to have a higher solidification time. It is going to solidify after a very long time. Getting the point? Yes. So the solidification time depends upon modulus. So you can easily write this thing as that the solidification time is equal to mold constant into modulus square. You can also write it like this. And he said if modulus is higher, solidification time is higher. Right? So obviously, what do you think? This total solidification time of the riser should be higher or the casting should be higher if it has to be compared? Obviously, the solidification time of riser has to be higher than that of the casting. Okay? That means, what does it mean? It means that the modulus of riser has to be higher than the modulus of casting. Okay, fine. Understood, isn't it? Modulus of riser is higher than modulus of casting. But how higher is a question, isn't it? You are simply telling me it has to be higher. But how higher? Is there any particular quantity? Yeah, so we can, approach it in a much better way. Yes, of course there is. Okay, so of course there is one quantity, and what is that? M of riser, modulus of the riser should be, or if modulus of riser is, if modulus of riser is equal to 1.2 times of modulus of the casting, that means it is higher than the modulus of casting by a factor of 1.2, then it is said, it has been experimentally found out actually, it is an experimental data. If this is the condition, then the risers are helpful. They work, they fulfill their purpose. Right? So it's a wonderful method of determining the not efficiency, I would say, the adequacy is the more appropriate word, whether the riser is going to work out or not. Okay. So again, I'm repeating once again that the modulus of riser, if is greater than modulus of casting by a factor of 1.2, then there are more chances, it has been found experimentally that the riser works out in these conditions. Getting the point? So this is nothing but the modulus method. Very good. Now, my friends, what will be the modulus of the cylindrical riser? Can you calculate that? Okay, we will calculate all together. So modulus, as sir you told us that it is volume divided by surface area. Fine, I accept. Then let us calculate the modulus for top cylindrical riser, no? That would be, let us simply just do something. So for top cylindrical riser, TCR I am writing as, volume, sir, it is nothing but pi by 4 d square h. I agree. And what is the surface area for top cylindrical riser? It was pi dh and only one side was actually, you know, participating in transaction of the heat energy. So surface area can be written as pi dh plus pi by 4 d square. Don't you think so? Yes, of course it is, sir. Now, sir, also we got to know that there was a relationship between diameter and height for top cylindrical riser, and what was that? It was d equal to 2h. Okay, fine. If so, that means if I have to minimize the surface area for top cylindrical riser, this condition has to be satisfied. Diameter should be equal to twice its height. So let us put down the values here. But I want everything in the terms of height, so I can write it as h equal to d by 2. Okay, I can write height is equal to d by 2, like this. Fine. Alright, so modulus for top cylindrical riser will be pi by 4 d square into h. Now what is h? D by 2, and divided by pi d h, pi d into d by 2 plus pi by 4 d square. Okay, pi by 4 d square. So let us solve pi by 8 d cube divided by pi by 2 d square plus pi by 4 d square. Yeah, this is what I have got. So modulus is going to be pi by 8 d cube divided by, this is, let us call it 6 pi d square divided by 8. Okay, so 8 and 8 got cancelled from here, d square and d cube got cancelled, pi and pi got cancelled. So what I am left with? I am left with d by 6. I'm left with d by 6 equal to m. So what does it mean? It means that modulus of a top cylindrical riser is d by 6, isn't it? So that means solidification time for top cylindrical riser is Cm times d by 6 and square of it. So we can see that this solidification time does not even depend upon the height in one way. I mean, just according to this expression. Alright. Of course, it depends upon the height because we have got this relation d equal to 2h. Only because of that we have got this expression. Otherwise, we couldn't have got this. So you can see this solidification time, as far as this expression goes, directly depends upon the diameter. So that means if you know the diameter of a riser, you can determine its solidification time. You don't have to calculate the surface area and the volume, isn't it? Don't you think it is a lot easier than calculating the volume and the surface area and dividing it and then squaring it and then multiplying it with a mole constant and to finally get the solidification time? It is a lot easier, right? So we have got one conclusion, that it is equal to d by 6, modulus is equal to d by 6 for top cylindrical riser. Now the same thing we will do for side cylindrical riser, and we will see what do we get. Okay, so I hope that you are following where we are heading, right? Yeah. So if you want to note it down, you can. So now we are going to do the same thing for side cylindrical riser, SCR. And what I can see is that D is equal to H was the given condition for side cylindrical riser for the minimum for minimum surface area. So modulus can be written as volume, again the same thing, pi by 4 d square h divided by surface area, which is nothing but pi d h plus twice of pi by 4 d square. You know why I'm multiplying it by 2, right? Because now you have understood. So this got cancelled and h is equal to d. So you can directly put down the values here. You can replace h by d. So d cube divided by pi d square plus pi by 2 d square. That means what we can write here as modulus is pi by 4 d cube divided by 3 pi by 2 d square, right? So d square gets cancelled with d cube, and pi got cancelled. This and this got cancelled. So what we can get is, it is d by 6 again, right? So that means modulus is equal to d by 6 again for also for side cylindrical riser, isn't it? So that means the solidification time is equal to Cm d by 6 and square of it. Again, we have got modulus as d by 6, isn't it? Just same as that of the top cylindrical riser. There is no difference at all, right? So again, it is a wonderful thing that you do not need to know the height of the riser. Even if in the problem, especially in the exams, they do not give you the heights. If they will directly give you the diameter, then also you can find out the modulus and the solidification time. This is what I mean to say, right? Very good. Now let us do the same thing for spherical riser. Let me tell you what is it. I'm directly going to give you the results now. Then if you have a spherical riser or spherical casting, right? For spherical riser or spherical casting, you know what is modulus there? It is again d by 6. Okay, for spherical casting and the riser, again it is d by 6. Similarly, you will find that the modulus for a cube, okay, for a cube, modulus for a cube of side A, I hope you can see from there. Is it visible to you? I am saying for a cube of side A. So there is a cube like this, and its side is A. Then the modulus will be equal to A by 6 for your cube, right? So why I am discussing about all these things? Because in exams, this method is going to be really helpful for saving time for you, okay? You will find that there are several problems given to you in exam where you have to compare the solidification time of a casting, of 3 castings. One is cube, another sphere, and another one is the cylinder. Okay, and you have to calculate the solidification time. You might have to find out the ratios. So there you don't have to waste the time in calculating the volume and the surface areas and then the solidification time. No, simply directly you can use these relations from here, d by 6, a by 6, like this, and you can directly get the answer. Okay, so it's a wonderful method to calculate the solidification time for your castings and the riser. Okay, so this was your second method called modulus method under the heading of riser design. Okay, I hope that you have followed, and that's all from the riser design. So let me summarize what we have done so far. We started our discussion with the shrinkage happening, and that led to one discussion where that why the riser is used and why the allowance, what is the difference between the functionalities of riser and these allowances. That we have understood, allowances are used only for solid shrinkages, where riser design is used for liquid contractions only. Okay, for liquid contractions only. Fine. After which we started discussing about the riser design. There are 4 conditions if you want your riser to work. There are 4 conditions you need to satisfy, which is the volume of the riser has to be greater than thrice of the shrinkage volume. What is shrinkage volume? It is volume by which the material contracts, right? Yeah. And the second condition was the solidification time. Solidification time is given by this method, this Kovalinov's rule. If you have seen, if you have noted down, it is known as Kovalinov's rule, right? And the third condition was the location of the riser. It has to be located at such a point, at such a place where it can provide extra molten metal to a part where it is needed the most. And the fourth is the shape of the riser. It should be able to supply, it should be able to hold the molten metal in molten state for a very long time, for which it has to have the least surface area for a given volume, right? And then we discussed that the cylindrical surfaces give the least surface area for the riser, and that's why we use. And we have seen there are 2 kinds of risers we can arrange as top cylindrical riser and the side cylindrical riser. And we have also found out the relationship between diameter and height. For top cylindrical riser, it is D is equal to 2h, and for side cylindrical riser, it's D equals to h. Right? And then we discussed about the riser design. There are two main methods. One is Keynes method, where you compare the functional, or you compare the riser against a graph to check the adequacy, whether it is going to work or not. If it falls on the right hand side of the curve, yes, it is, you're going to get a sound casting, otherwise not. And the second method was the modulus method, where which is based upon the Kovrinov's rule, which is V by A is considered to be the modulus, and it is considered that whenever the modulus of something, suppose of the riser, is higher than that of the casting, then the solidification time of that riser is going to be higher than that of the casting, which is going to work. That is what we require, isn't it? And also it has been found experimentally that modulus of the riser has to be equal to 1.2 times of modulus of the casting. Then in that case, the riser is going to work for most of the times. Okay, it has been found experimentally. And then we calculated the modulus for side cylindrical riser, top cylindrical riser, and also for a spherical casting or a riser, and then for a cube. Cube can also be a riser or a casting, whatever, but you can use this relationship anywhere, okay, if it is going to solidify. So that is all that we have discussed so far. So friends, we have just now seen, we have learned about the riser design and the solidification time. Solidification time means the Kovrinov's rule. This is what I am talking about. So let us solve few questions upon that, and let us try to understand how those questions have to be solved. Right, and these problems are very prominent in your GATE examination. So let us have a look here. Okay. So the first question says, alright friends, so you can see this is one problem I have shown to you, and it says a cylindrical riser is to be designed such that, and what are the requirements of that riser, that length is equal to 1.25 times its diameter, and the casting is a square plate of side 10 centimeter and thickness is 7.5 centimeter. The mold constant Cm is given to you as 16 minute per centimeter square. You have to determine the length of the riser such that it takes 30% longer than that of the casting to solidify. Okay, so what we need to do first of all is that we will find out the solidification time for the casting first, right? Okay, so let us start. Tau for casting, Tc stands for casting, and Cm V by A square. Now Cm is given to you as 16 minute per centimeter square. Volume of, the square plate would look something like this. Like this. Okay, try to understand. This is freehand figure. So this is 10 and 10, and the thickness is 7.5. So the firstly the volume is okay, fine. Volume is nothing but 10 into 10 into 7.5. Now the surface area, for that, it's there are two surfaces for each surface. I mean, there are two identical surfaces. So if I consider 10 by 10, there is one more 10 by 10 on the other side. So that's why 2 multiplied by 10 plus this one, which is 10 into 7.5, 10 into 7.5 plus, right? There is one more 10 into 7.5 here. So 10 into 7.5. Like this. Okay. And the complete square of it. Do not forget to square this term V by A, because it's a very genuine mistake. It's a very common mistake. People forget to square V by A. Okay, ratio. So when you will solve for this, you will get tau for casting as, I have already the answer with me. It's 36 minutes. If you solve everything, you will arrive at 36 minutes, right? Now, this is the solidification time for the casting. Solidification time of the riser is 30 times more. I'm sorry, not 30 times, 30% more, right? 30% higher than 36 minutes. So, tau for riser will be 1.3 times 36 minutes. Isn't it? Yes. So, it will come out to be 46.8 minutes. So, it will be 46.8 minutes. Right? Now, we have to find out the dimensions of the riser. So, using the same thing, so 46.8 and CM's value is 16 and V by A. So, you know, you have read in modulus method that V by A, this modulus can be simply replaced by D by 6, isn't it? So, I am going to do the same thing here. Let us write down D by 6 and square of it. Okay. Now, from here you can determine the value for D, and diameter will come out to be, I have a ready answer with me, it is 10.26 centimeter, right? So this is the diameter of the riser, fine. But what is actually required, you have to determine the length. So what is the length or the height? Let us call it L, length. Length is 1.25 its diameter. So 1.25 times of 10.26. Again, I have a ready answer with me. You can calculate that and you will get the answer as 12.825 centimeter. 12.825 centimeter. So this is your answer, my friends. Okay. So in this manner, this question can be solved. So it's pretty easy, pretty simple. The only thing is that you need to use the logic. That's all. Right? So let us move to the next question. We will solve one more question of similar kind. Right? Alright friends, so have a look here. This is a very, very simple problem, but you can find these kinds of problems being asked in GATE several times. So just to give you a feel, I am giving this problem to you. You can solve it very easily, very conveniently. In the casting, it takes 155 seconds for a cube of side 50 mm to solidify. Then determine the value of cm in second per mm square. Alright. So for this, what you have to do is simply consider the Kovalinov's rule. T is equal to cm v by a and square of it, and it is a cube, right? So it takes 155 seconds. Cm's value has to be found out, and the volume is going to be. So what you can do is either you can write 50 into 50 into 50, or simply you can take the ratio v by a as a by 6. It is going to give the same value. You can see over here. Suppose I take the volume, which is 50 by 50 by 50, and the surface area will be 60 into 50 square. That means 60 into 50 into 50 and square of it. So you can see these will get cancelled out, and eventually you are left with 50 by 6 only, which is a by 6, right? Right. So from here, if you find out the value of cm, it will be 155 into 6 square by 50 square. Right, and when you will solve for this, I have a ready answer with me, and it comes out to be 2.232. Okay, it will come out to be 2.232 second per mm square. So this is going to be your answer. This was a simpler problem, but since these kinds of problems are very prominent in a GATE exam, and yeah, from this particular topic, so that is why we have included that. I hope now it's clear, and you have followed the topic completely. Okay, so that is all for now. Thank you.